In 1947, three men in a quiet laboratory in Murray Hill, New Jersey, did something that sounds almost absurd when you say it out loud. They took a tiny sliver of a material, a crystal, barely the size of your thumbnail, and they made electricity think. Not metaphorically, not poetically, literally. They created a device so small, so unassuming, that most people walked right past it without a second glance. It sat on a lab bench cluttered with wires and instruments and half-finished experiments. It did not look like the future. It did not look like anything at all. And yet, that object, that single, almost invisible invention, is the reason you are watching this video right now. It is the reason your phone exists. It is the reason the internet works. It is the reason planes can land in thick fog without a single human hand on the controls. The reason surgeons can see inside your body without cutting you open. The reason that satellites can orbit a planet and beam information back to a device in your pocket in the time it takes you to blink. It is the reason you can stream a movie in a place where, 60 years ago, there was nothing but open field. It is the reason you can talk to someone on the other side of the world in real time for free. It is the reason that artificial intelligence, the thing every headline is screaming about right now, is even possible. The transistor, the most important invention in human history. And I know how that sounds. The most important? More than the printing press? More than the steam engine? More than electricity itself? Yes. And by the end of this video, you will understand exactly why. But here is the thing nobody tells you. Every single one of those miracles, every convenience, every marvel of modern life that you have come to take completely for granted came with a price. And some of that price we are still paying, right now, today, without fully understanding what it is. This is the story of the transistor. The invention that compressed 50 years of human progress into a single lifetime, and the hidden, uncomfortable, deeply human cost of the future it built. To understand why the transistor changed everything, you first have to understand what the world looked like without it, because the world before 1947 was not a world that could do what we do now, not even close. Before the transistor, if you wanted a machine to process information, to calculate, to communicate, to compute, you needed something called a vacuum tube. Now, a vacuum tube is not complicated in concept. It is essentially a glass bottle, sealed, with no air inside, with electrodes in it. It works by heating a metal filament called a cathode until it glows red hot. When it gets hot enough, electrons begin to stream off of it, invisible but electrically real, and fly across the vacuum toward another electrode. And by controlling that stream of electrons, using a third electrode as a kind of gate, you could do two things that matter enormously. You could amplify a signal, making it stronger, and you could switch a circuit on or off. Those two things, amplification and switching, are the two fundamental operations that make all electronics possible. Without them, you cannot build a radio, you cannot build a telephone, you cannot build a computer. And for decades, the 1920s, the 30s, the early 40s, vacuum tubes were the only way to do it. But here's the problem with vacuum tubes, and it is not a small problem. They were enormous compared to what would come later. Each one was roughly the size of a human finger. They were made of glass, which meant they shattered if you dropped them, or bumped the equipment too hard, or sometimes for no apparent reason at all. They generated tremendous heat because of that glowing filament, which meant the machines that used them needed constant cooling, and they burned out constantly. A vacuum tube might last a few hundred hours before it failed and had to be replaced. In a machine that used thousands of them, that meant someone was replacing tubes almost every single day. The most extreme example of this was ENIAC, the electronic numerical integrator and computer, one of the first fully electronic computers ever built, completed in 1945 for the United States Army. ENIAC used 18,000 vacuum tubes. It filled an entire room. It consumed roughly 1,500 kilowatts of power, enough electricity to power a small neighborhood of houses running continuously. And it broke down so frequently that the technicians who maintained it spent more time fixing it than it spent actually computing anything. ENIAC could perform roughly 5,000 addition operations per second. That sounds impressive until you realize that a single chip inside your smartphone right now can perform billions of operations per second. We're talking about a difference so vast, it's almost impossible to visualize. And here's what makes the story even more compelling. The people running the most advanced technology in the world at that time knew vacuum tubes were a dead end. They knew the heat, the size, the constant failure rate, it was all unsustainable. If computing was going to get bigger, if communication was going to get faster, if electronics was going to become something more than a niche technology used by laboratories and the military, something had to change. The question that kept engineers at places like Bell Labs, IBM, and the military's own research divisions up at night was deceptively simple. What could replace the vacuum tube? For years, nobody had a convincing answer. Enter Bell Labs, Murray Hill, New Jersey, a sprawling campus that in the 1940s was arguably the single most powerful research institution on the planet. Bell Labs was funded by AT&T, the American Telephone and Telegraph Company, which at that time held a near-total monopoly on telephone communication in the United States. AT&T's mandate to Bell Labs was straightforward on the surface: make communication better, make it cheaper, make it faster, make it reach more people. But better at Bell Labs did not mean small improvements. It did not mean tweaking what already existed. It meant reinventing things from the ground up. Bell Labs had a culture, almost a religion, of fundamental research. They hired the best scientists in the country and then, essentially, left them alone to think. And what they produced over the decades was staggering. The telephone itself had roots in Bell's predecessor companies: the laser, the solar cell, the Unix operating system, C programming language, and yes, the transistor. It was here, in the mid-1940s, that a man named William Shockley became consumed by an idea. Shockley was a physicist, not just talented, genuinely brilliant. He had already made significant contributions to the war effort, working on radar systems and other military technology. He was confident, ambitious, and by nearly every account from the people who worked alongside him, extraordinarily difficult. He had a theory, a conviction really, that it was possible to control the flow of electricity through a solid material, not a gas inside a sealed glass tube, a solid, something like a crystal. If you could do that, if you could amplify and switch signals using a piece of solid matter, you would eliminate every weakness of the vacuum tube in one stroke. No glass to shatter, no filament to burn out, no heat to manage, no size problem. He called it solid-state electronics, and in 1945, he pitched the idea to Bell Labs leadership, and they gave him a team and a budget and told him to make it happen. For the next 2 years, Shockley worked on it, and for the next 2 years, he failed. Not quietly either. His early theoretical models were incomplete. The physics of how electrons behaved at the surface of a semiconductor, the boundary between the material and the air, turned out to be far messier than he had predicted. Something called surface states was sabotaging his designs. Electrons were getting trapped at the surface in ways that no one fully understood, and they were killing the signal before it could be amplified. Shockley tried approach after approach. None of them worked. And Shockley, who was not a man accustomed to failure, did not take it gracefully. So Bell Labs did something quietly diplomatic. They did not fire Shockley. They did not shut the project down. The potential was too significant for that. Instead, they gently, almost imperceptibly shifted the center of gravity. They let 2 other scientists, 2 men who had been working alongside Shockley but had been largely overshadowed by his personality, take the experimental lead. Their names were John Bardeen and Walter Brattain. Bardeen was a theorist, quiet, almost painfully so, the kind of man who could sit in a room full of people and say almost nothing and still be the most important mind in the space. Brattain was the experimentalist, hands-on, intuitive, gifted at making things work in the lab in ways that pure theory could not predict. Together, with Shockley still circling the project from a distance, the 3 of them were about to stumble into the single most consequential discovery in the history of modern technology. December 16, 1947. It was a Friday. late in the afternoon. Most of Bell Labs had already gone quiet. People were heading home for the weekend. But Bardeen and Brattain were still in the lab, hunched over an experiment they had been refining for weeks. The setup looked almost laughably simple to an outsider. A small piece of germanium, a grayish, slightly metallic element that is what scientists call a semiconductor, meaning it conducts electricity, but not as well as a metal like copper or gold, not as poorly as an insulator like rubber or glass, somewhere in between. And that in between, that ambiguity, turned out to be exactly where the magic lived. On the surface of this germanium, Bardeen and Brattain had placed two tiny gold contacts, thin wires, barely touching the crystal. One of them was the emitter, the other was the collector. They passed a small electrical current in through the emitter, and then they measured very carefully with sensitive instrument what came out the other side. The current that came out was dramatically larger than the current that went in. Not by a little, not by 10% or even double, by a factor of nearly 250. They had just amplified an electrical signal without a single vacuum tube, using nothing but a piece of crystal and two pieces of gold wire pressed against its surface. Bardeen and Brattain looked at each other across the lab bench. They did not cheer. They did not shout. By most historical accounts, the moment was quieter than that. More like a shared, slow exhale. The kind of silence that comes when two people simultaneously realize that what they have just done is not just a successful experiment. It is a door opening onto an entirely different world. What they had built was called a point-contact transistor. The word itself was a portmanteau. Trans for transfer, sister from the Latin sistere, meaning to stand or to place. Transfer and stand. It transferred a signal, and it stood where a vacuum tube used to be. On that Friday afternoon, in that quiet lab, Bardeen and Brattain had not set out to change civilization. They had set out to solve a physics problem. But the thing about truly fundamental discoveries is that their consequences are almost always invisible at the moment they happen. The people who make them rarely understand, not fully, not yet, what they have actually done. The transistor was not yet small, it was not yet cheap, it was not yet reliable. It was a proof of concept, a seed. But seeds, given enough time and enough sunlight, become forests. Now, if you are not a physicist, if the words semiconductor and germanium already made your eyes glaze over, do not worry. You do not need to understand the deep quantum mechanics of how a transistor works to grasp why it matters. But you do need to understand the idea, the core principle, because it is, at its heart, almost beautifully simple. Think of electricity like water flowing through a pipe. A transistor is like a faucet. You turn a small handle, a tiny amount of force, a tiny input, and it controls how much water flows through a much larger pipe. A small signal controls a large one. That is the transistor. At its most fundamental level, it does one thing. It uses a small electrical signal to control a large one. But here's the part that makes that one thing revolutionary. If you can amplify a signal, make it stronger, you can send information over longer distances without it fading out. That is how radios work. That is how telephone calls travel across oceans. If you can switch a signal on or off, representing a 1 or a 0, you can encode information. Binary, the language of every computer ever built. And if you can do that switching not once, not 1,000 times, but billions of times per second, in something smaller than a grain of sand, you have a computer, you have the internet, you have GPS, you have medical imaging, you have the entire digital infrastructure of modern civilization. The transistor is not just a component of modern technology, it is not one piece among many, it is the foundation, the bedrock. Remove it, imagine, for a single second, a world in which the transistor had never been invented, and everything collapses. Every screen goes dark, every signal dies, every system that depends on the processing, storage, or transmission of digital information stops functioning, which, in the 21st century, is almost everything. Your bank account, gone. Your medical records, inaccessible. The power grid in its current form, unmanageable. Air traffic control,
blind. The transistor is not something we use, it is something we depend on, completely, utterly, in ways most people have never once stopped to think about. Here's what happened after that Friday in December 1947. And pay close attention, because it happened fast, faster than almost any technological revolution in human history. 1950s, the transistor shrinks. Engineers figure out how to make them smaller, more reliable, cheaper to produce. The first transistor radios hit store shelves, portable, affordable, revolutionary. For the first time, ordinary people hold a device in their hands that contains no vacuum tubes at all. Consumer electronics as an industry is effectively born. 1958, two inventors, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor, independently develop something that will change everything again. They figure out how to etch multiple transistors onto a single piece of silicon. Not one transistor, not 10, eventually thousands, all connected, all on a chip no bigger than a fingernail. It is called the integrated circuit, and it does to transistors what the assembly line did to cars. It makes them absurdly cheap to produce at scale. 1965, a man named Gordon Moore, co-founder of what will become Intel, publishes an observation that will shape the next 60 decades of technology. He notices that the number of transistors engineers can fit onto a single chip has been doubling roughly every 2 years, and he predicts, boldly, almost recklessly, that this trend will continue. This becomes known as Moore's Law. It is not a law of physics, it is a prediction, an expectation, a target that the entire semiconductor industry organized itself around hitting, and for decades it held. 1971, Intel releases the 4004, the first commercially available microprocessor, a single chip that contains 2,300 transistors and can be programmed to do different tasks. It is, by modern standards, slower than a basic calculator, but it is the direct ancestor, the genetic origin of every processor running in every computer, phone, tablet, and server on Earth right now, every single one. Late 1970s and early 1980s, personal computers began arriving in homes, the IBM PC, the Apple Macintosh. For the first time in history, individuals, not corporations, not governments, not universities, have access to meaningful computing power. The idea that a computer is something that belongs in your house, on your desk, within your reach, that idea simply did not exist before transistors made it possible. 1991. The World Wide Web goes live. Tim Berners-Lee, working at a physics lab in Switzerland, creates a system that allows anyone with a computer and an internet connection to share and access information through a simple interface. The internet had existed before this, in military and academic forms, for decades, but the web, the thing that made it usable by ordinary people, transformed it into a global commons. And the transistors powering the servers, the routers, the cables, there are now billions of them running without pause every single day. 2007, Apple releases the iPhone. It is not the first smartphone, but it is the one that convinced the world that a computer powerful enough to run the internet, play video, take photographs, and navigate by satellite can fit inside your pocket. The transistor count in that first iPhone's processor, around 620 million. 2024, a single modern chip, like the one inside an iPhone 15 or a high-end Android device, contains over 15 billion transistors. 15 billion in something smaller than your fingernail. From 2,300 transistors in 1971 to 15 billion in 2024. That is not gradual progress. That is not an incremental improvement. That is a civilizational leap, a compression of potential, of capability, of power that in any other field of human endeavor would have taken centuries. It happened in 50 years, and it was all built on the back of one invention made by 3 men on a Friday in Azalon, New Jersey. But here's where this story gets uncomfortable. Because for every miracle the transistor gave us, and there are many, there was a cost, sometimes visible, sometimes hidden, sometimes one we chose, consciously or not, to look away from, and sometimes one we are only beginning to fully understand right now. the environmental cost. Manufacturing transistors at the scale we do today is one of the most chemically intensive and water-hungry industrial processes on the planet. A single modern semiconductor fabrication plant, a fab, can consume upward of 3 to 5 million gallons of ultra-pure water per day. Not regular water, water that has been filtered and purified to a degree of purity that exceeds anything you have ever encountered. Because even a single impurity, a single molecule out of place, can ruin an entire batch of chips. In regions where water is already scarce, parts of Arizona, Taiwan, parts of South Korea, the construction of fabs has become a point of genuine tension between the tech industry and local communities who need that water to drink, to irrigate, to live. And then there's the contamination. The chemicals used in chip manufacturing, solvents, acids, gases, are toxic. In the early decades of the industry, the 1960s and 1970s, environmental regulations were far weaker than they are today, and the companies building fabs were not always careful about how they disposed of their waste. The result is one of the most polluted regions in the United States. Silicon Valley itself, the birthplace of the personal computer, of Apple, of Google, of the entire consumer tech industry, sits on top of a contamination zone. Trichloroethylene and other toxic chemicals seeped into the groundwater beneath dozens of sites in Santa Clara County before anyone fully understood what was happening. The EPA has designated multiple locations as Superfund sites, places that require decades of cleanup and tens of millions of dollars to remediate. The irony is almost too neat to be believed. The place that invented the digital future
poisoned the ground it was built on. The human cost. The global semiconductor supply chain is vast, and most of it is invisible to the people who consume its products. From the mines that extract the raw minerals, cobalt, tantalum, rare earth elements, to the fabrication plants, to the assembly lines where chips are packaged and tested. Millions of people work in this chain. Many of them work long hours, in difficult conditions, for wages that would not sustain a family in the countries where the chips are ultimately sold. This is not unique to the semiconductor industry. It is a feature of almost every hardware industry in the modern economy. But the transistor, the invention that made our digital lives possible, did not arrive in our pockets and on our desks without human hands, human labor, and human sacrifice at every stage of its creation. The social and psychological cost. And then there is the cost that is the hardest to quantify, but arguably the most significant of all. What the transistor-powered world has done to us, to human attention, to human behavior, to the way we think. The same technology that allows a doctor in New York to consult with a specialist in Tokyo also allows a teenager in Lagos to spend 6 hours a day watching algorithmically curated content designed by teams of engineers using transistor-powered computers to be as psychologically compelling as possible. Designed, in other words, to be addictive. The platforms that democratized information also democratized misinformation. The tools that gave individuals a voice also gave individuals the ability to harass, manipulate, and deceive at scale. The devices that put the sum total of human knowledge in our hands also put the most engineered, the most attention-fragmenting media ever created in those same hands. We did not consciously choose that trade-off. No one sat in a room in 1947 and said, "Let us build something that will one day fragment human attention and reshape the psychology of an entire species." But that is, in part, what happened, quietly, gradually, one transistor at a time. And here is something most people do not know. Not everyone celebrated the transistor's arrival. Not everyone looked at the trajectory of solid-state electronics and thought, yes, this is the direction we should go without reservation. Some of them looked at that trajectory and felt something closer to unease. In the 1960s and 70s, as automation powered by transistors began to displace jobs, first in manufacturing, then in clerical work, then in increasingly complex domains, a small but serious group of technologists and philosophers began asking questions that the industry, moving at the speed it was moving, did not want to slow down to answer. Who controls the machine? Who benefits from its outputs?
and what happens to the people it leaves behind. One of the most notable voices was Joseph Weizenbaum, a computer scientist at MIT. Weizenbaum had actually built one of the earliest chatbots, a program called ELIZA that simulated a therapist by rephrasing what users typed back to them in the form of questions. It was crude, it was a joke almost by modern standards, but Weizenbaum was horrified by the reaction it provoked. His own secretary, someone who knew it was a program, asked to be left alone with it as if it were a real therapist. People trusted it, they confided in it. That experience shook him, and in 1976, he published a book called Computer Power and Human Reason, in which he argued that society was handing over more and more of its decision-making, its judgment, its authority, to machines, without pausing to ask whether that was wise, whether the speed of technological progress was outpacing our ability to understand its consequences. He was not anti-technology, he was anti-blindness, and very few people listened. Others pushed in a different direction. Early internet pioneers like Vint Cerf advocated for the technology to be built with openness, with access, with the public interest in mind, not just profit margins. Some of these voices shaped policy, many did not. The transistor was never going to be stopped. The economic incentive was too powerful, the utility was too obvious, the momentum was too great. But the people who paused, who asked not just can we, but should we, deserved to be part of this story, because they were right to ask, and in many cases, the answers they warned about are the ones we are living with today. Let's look at the numbers, because the scale of what the transistor made possible is almost impossible to grasp with words alone. You need to see the data. Over 1 sextillion transistors have been manufactured since 1960. 1 sextillion. That is a 1 followed by 21 zeros. More transistors have been made by human hands, by human machines, than any other manufactured object in the history of the species. It is not close. Nothing else comes within an order of magnitude. Global semiconductor industry revenue exceeded $600 billion in 2023. That is larger than the global film industry, larger than the music industry, larger than most consumer goods sectors combined, and it is growing. The energy footprint of the transistor-powered world is enormous and expanding. Data centers, the buildings full of servers that run the internet, that store your photographs, that process your searches, now consume roughly 1 to 2% of global electricity. That number has been climbing steadily, and with the rise of AI, which requires massive amounts of computational power, it is expected to climb much further. And Moore's law, the prediction that transistor density would double every 2 years, held for over 50 years. But physicists and engineers are now approaching the fundamental physical limits of how small a transistor can be made. At some point, and some believe that point is already here, you simply cannot shrink them any further. Atoms have a size. Physics has a floor. What happens when we hit it is one of the biggest, most consequential open questions in the history of technology.
So where does this leave us? The transistor's dominance is not over, but the era of simply making them smaller and faster, the era that Moore's law defined, is nearing its end. And what replaces it will shape the next 50 years the way the transistor shaped the last 50. Quantum computing uses not transistors, but qubits, particles that exploit the strange, counterintuitive rules of quantum mechanics to exist in multiple states simultaneously. A quantum computer, if it works at scale, could solve problems that would take every transistor-based computer on Earth longer than the age of the universe to crack. Drug discovery, materials science, climate modeling, and, unsettlingly, the ability to break the encryption that protects virtually all digital communication and financial transactions today. Neuromorphic chips are being designed to mimic not the sequential step-by-step logic of a traditional computer, but the parallel associative way a biological brain processes information. They promise to do what AI does today: pattern recognition, learning, decision-making, at a fraction of the energy cost. Intel and IBM are already building prototypes. And artificial intelligence, the technology that is reshaping every industry right now, runs at its core on transistors. Billions of them, processing trillions of calculations every second, inside chips that were designed specifically to handle the mathematical demands of machine learning. The transistor is not being retired. It is being aimed at a new kind of problem, a new kind of intelligence. The invention that pushed humanity 50 years ahead is now powering the technology that could do it again. In 1947, three men made something the size of a thumbnail, and they set in motion a chain of events that reshaped civilization. They did not plan for the internet. They did not plan for smartphones or social media or artificial intelligence. They were solving one problem: how to amplify an electrical signal without a vacuum tube. And the world they accidentally built from that single solution is the world you live in right now. The transistor gave us medicine that saves lives. It gave us communication that connects billions. It gave us tools to understand the universe in ways no generation before us ever could. But it also gave us pollution we are still cleaning up. It gave us systems that concentrate power in ways we are still reckoning with. And it gave us a world so saturated in information, so engineered for engagement, that many of us struggle, quietly, privately, to think clearly in it. Every great invention is a trade-off. The question is never simply what did we gain? The question is always, did we look carefully enough at what we were willing to lose? The transistor gave us the future. Whether we are ready for it, whether we have earned the right to wield what it made possible, that is still an open question. And the answer, in large part, depends on whether we finally start asking it.